Hello and welcome to this session of Introduction to Autonomous Systems. If you have been following the thread of the content, you would have recalled that in the last segment we had introduced the idea of probability calculus, and at the same time we also had talked about the idea of certainty factors and the construction of MB and MD as two primary parameters which capture the opinion of an expert. In the present session, we will take this idea forward and introduce another concept of probability, what is called the conditional probability. So, let us begin today's session. Concept of conditional probability is essential for working with probability calculus and is defined as below. What it says is that if an event y has occurred or there is a certainty that it will occur at some point in time in future, the probability that another event x will also occur is called the conditional probability and is denoted as P in parenthesis x vertical bar y. The implication of this symbol is that given y, what is the probability of x occurring? So, this brings in an idea of condition. The reason why this becomes an important concept for our uncertain reasoning is mainly because when we are looking at an event or a particular hypothesis being true or not true, and we start collecting evidence to either support or refute that hypothesis, the events which are in the form of evidences are essentially y, whereas the hypothesis that we are talking about is x. So, essentially what we are saying is that what is the probability of this hypothesis x if there is an evidence which is going to come or has come which is y. So, this is how we look at this whole problem of conditional probability. We will also note that as we go along, this will get used directly as part of our probability update rule and an important element of uncertain reasoning. So, let us proceed. Mathematically, this is nothing but the ratio of the intersection of these two events x intersection y, the probability of that intersection divided by the probability of y. So, it is equivalent of saying that per unit of probability of y, what is the probability that x will occur because y has occurred. So, x intersection y represents that particular segment of our probability calculus where we have overlapping events, which means x and y are now overlapping events, and there is an area which is common, and that common area we want to know how it is in relation to the area of the event y itself. Now, of course, we see that while this would be 0 for non-overlapping events, it will become non-zero for overlapping events, which is also as per our intuitive understanding and expectation. Conceptually, if we imagine that whole universe has shrunk to the size of only y, which means y is the only event which occurs in that universe, there is no other event, then what we are essentially saying is that what percentage of y is x, which means this p x bar y is nothing but a fraction or a percentage of y which is left, because if y is the only event and the whole universe, the probability of y becomes 1, and then what is left is the probability of x occurring. So, as you can see, the area in the middle is the intersection between x and y, and this intersection y as a ratio of the area of y is nothing but our conditional probability p in parenthesis x vertical bar y. So, or if you want to talk about areas, that is the ratio of the shaded area versus the area of the event y. Let us now bring in another idea of independence in the light of the conditional probability that we have seen. Now, independence, as we have introduced this idea some time back, essentially says that x and y are non-overlapping events. Now, that is the very first or the basic interpretation of independence, that if x and y are non-overlapping, then obviously x will occur independent of y, and these two are two independent events. But we are not really looking at those kind of scenarios. In our cases, there are going to be actually cases where there will be events which will be overlapping, which means we are looking at an evidence which will have something to do with the hypothesis, or looking at an event which will have an intersection with another event. So, let us now examine this in some detail as to what exactly we mean by independence in such context and what are the implications. So, the way we say is that independence is not really directly connected with the non-overlapping behavior. We now move to another concept. We say that x and y are considered to be probabilistically independent if conditioning on one leaves the probability of other unchanged. So, let us start with the expression leftmost. So, x and there is a orthogonality symbol. So, we say that x and y are independent when x is orthogonal to y, which means y has no projection in x direction, is our understanding from geometry and trigonometry. So, we just make use of the same understanding analogy to say that independence of x in relation to y ultimately makes x orthogonal to y. That is equivalent to the conditional probability of x with respect to y is same as the probability of x itself, which means even if I bring in the event y, the probability of x does not change. And this is a bidirectional relation. So, we say that if x is orthogonal to y, converse is also true, that y is orthogonal to x, so that probability of y in the presence of event x also remains unchanged as probability of y. So, this is the first step that we take in this direction of trying to capture the whole idea of independence. So, what we are saying is that x and y become orthogonal, and that presence of y has no impact on what is the probability of x occurring or not occurring. Now, of course, the simplest example of any independence of events is the gambling event, or for example, a roll of a dice. What we say is that if you roll a dice once and you get a number, that has no impact on the next roll of dice. So, same number could come or a different number could come. There are no implications of that if you have a particular number in the previous roll, that number may not come in the next roll or will again definitely come. There are no such connections. So, these are completely independent events. Of course, the converse of this would be that when the events are dependent on each other, so we say that if there is an event which comes true, which means which happens, it will change the probability of the next event coming true, which means now there is a dependence of the next event x on the event y occurring. So, this concept of dependence can be explained through the basic example of drawing of cards from a deck of cards of a specific suit, and you will realize that there are 52 cards and in each suit there are 13 cards. So, the first card of being a particular suit, the probability would be 13 by 52 or 1 by 4. However, once we have removed that card, the probability of the second card being of the same suit would be different, because there are only 51 cards left and there are only 12 cards of that particular suit left. So, the probability will become 12 by 51, and you can see that the fact that the first event has come true has changed the probability of the second event. So, they are dependent on each other, and in some sense you can say these are overlapping events. Now, let us generalize the idea to say that in the context of two events x and y, suppose there is a third event z which occurs. What happens? Let us say that we are talking about the same physical domain and the events are of a similar kind. So, if you say that you have an event x and y, we already know from our conditional probability and the concept of dependence as well as independence that there will be some kind of a probability for x occurring if y has occurred based on the intersection of x and y. But now suppose there is another event z, how do we introduce this? Let us see what we can do. So, let us write an idea which says, supposing I am saying x orthogonal to y. Now, I am saying that x and y were dependent on each other, and now there is another event z on which x is dependent. So, it can be shown that in the presence of event z, x and y can be shown under certain conditions to become orthogonal. So, which means that if you have another event z occurring on which also indicates whether x will occur or not, then it is possible for us to say that x then becomes independent of y, but it is conditional on z being present. So, which means that under the condition that z has occurred, x will become independent of y, which was initially not. Of course, we will realize that if z is an empty or a null set, then the above relation will simply degenerate to the conditional probability of, which means if z becomes 0, this is nothing but your probability of x upon in the light of event y occurring. Now, when does this happen? It is not a general scenario, but there are situations where such a thing will happen and we need to understand those. So, if we want to ask this question, that conditional independence holds good when event z tells us everything about event which y will tell about x, which means whatever y is telling us about x, z is telling everything, all the same thing about x. So, indirectly what we are saying from a physical argument perspective is that event y is really redundant, which means we do not really need y, because whatever y was telling about x has already been told by z. So, you do not need y. So, x has now become completely independent or orthogonal of y, but in the presence of z, not otherwise. So, what we are saying is that x and y are dependent, but under the special condition that whatever is the intersection of x and y is the same as the intersection of x and z, so that you do not really need y, you can take out the y from your whole process. So, let me give you an example. Suppose we have an approximate but less expensive test y for a particular disease x. So, we say that if you conduct a test y, it tells us something about the disease x, that the probability of what x could be. For example, if you do a blood test and it shows that you have low hemoglobin, the test could be that you have iron deficiency, that could be the disease for some reason, there could be some issue which is causing iron deficiency. Now, suppose you do a more accurate test which directly deals with the disease and say yes, not only there is a issue of anemia, but it is related to this particular condition which is there in the body. So, now you realize that the confirmation of it being disease X is dependent on the more accurate test Z, and now we can simply throw out Y and say we do not really need Y to conclude about X, we already can conclude about X based on the Z. So, this is the implication of this conditional independence scenario. This is also sometimes called the screening of X from Y by Z. So, let us look at the formal theorem which can be used to solve problems. So, there are two theorems. One theorem is of total probability, what we call the probability of universe, as sum of all the probabilities of an event A, all the elements which are there part of that set, given that union of all these AIs constitute your universe U. We also say that these events are independent, which means AI intersection AJ is 0, and we say probability of B is sum of the probability of B intersection AI, B being another event, given that AI is not 0, which means it is not a null set. There is also what we call a chain rule, which says that conditional probability of C in the presence of event A can be written as conditional probability of C in the light of event B multiplied by the conditional probability of B in the light of event A plus their negations, that probability of C in the light of not B and probability of not B in the light of event A. So, we say that given events A, B, C, A and C are independent of given B. So, this is how the two additional theorems are brought in to help us with solving our problems which will involve use of conditional probability. Now, of course, so far what we have discussed about the probabilities is essentially related to discrete events in the real world, which means events which are discrete, one at a time, episodic. But in real world, we also have to deal with variables that exhibit a similar behavior, and these are obviously called the random variables. So, we also now need to talk about the same ideas, but in the context of variables, continuous variables instead of discrete variables. So, we define that a random variable is that which reports an outcome of some measurement process. For example, you have a calibration of a particular sensor where you give a particular input and you measure a voltage output. For example, it could be a simple LVDT where you are trying to calibrate it for the position measurement, and so you put it at a different positions, the plunger, and you measure the voltage. Now, because this variable though is continuous, there are discrete elements that you are measuring, which means at specific values of input you are measuring the response of that particular sensor, and it can still be considered as a kind of a state which is discrete, it has discrete elements. Of course, instead of this scenario, we could have a continuous curve or a function, continuous function. In that case, we need to bring in an additional concept to understand the random variables, and that is what we call the probability density function. So, we define this probability density function over variable x, which assigns a weight or a measure to each possible value of x and can be represented through a finely partitioned histogram. Although it is realized that the density is not the probability function itself, it can be used to generate probabilities of any event x if the function is such that first of all it is non-negative, which means it represents the concept of area that we have talked about as part of our probability calculus, number one. And number two is that this function is such that over the complete domain over which it is defined, it integrates to 1, which means it also represents the universe. So, if it satisfies these two conditions, that it is non-negative and its sum total adds up to 1, then this same function can also be used as a probability density function and can be used to generate probabilities through integration. So, we say that above function can also be used to define cumulative probability density. There is another term which is called, where we say uppercase f of x as probability of uppercase x less than or equal to a lowercase x, which is nothing but an integral of all values up to some number x in the whole domain of the variable x. So, to conclude this session, conditional probability brings out the overlap between two events and helps in assessing the level of dependence between them, number one. And number two, the concept of conditional independence provides a method to choose evidences that are more useful and thus have a lot of practical applications. With that, we come to the end of this particular segment, and in the next segment we will introduce another idea which will take this conditional probability and make use of it in the context of uncertain reasoning. So, with that we close this session. Bye for now. Thank you and see you in the next session.